Hello, my name is Mark King, and you are listening to the seminar series that I sponsor in my role as Atlantic Canada representative of the International Association of Hydrogeologists, the IAH. In this capacity, we solicit seminar presentations from speakers all over the world. The general topic is groundwater and hydrogeology, but within that field, the talks can vary over a wide range, from water supply to geochemistry to remediation to the fate and transport of groundwater contaminants and beyond. And at times we may also stray outside the bounds of hydrogeology when a particularly interesting technical topic or speaker comes our way. Welcome to our seminar series. My guest today is Sam King. Sam's presentation is not related to hydrogeology, but I'm sure you're going to find it interesting. Sam is a physicist, and he recently completed a Ph.D. in particle physics at the University of British Columbia. He conducted his doctoral research at the famous Large Hadron Collider, located on the border between France and Switzerland. I've spoken with Sam many times about his research, and I think you're going to appreciate the way he takes a very intimidating subject like particle physics and makes it quite understandable. By the way, I should mention that Sam's an accomplished musician and writer of music, and that our theme music is actually a snippet from a piece of music that Sam wrote and recorded. And I should also mention that Sam happens to be my son. Sam, welcome to the IAH seminar series.
All right, well, thank you very much. So I am going to go through a few slides today and sort of give a bit of an overview of what some of the main ideas behind particle physics are, and in particular how one might be able to search for new particle physics models, evidence for these models at a hadron collider. So this is something that I've been working on for the past few years, and so hopefully I've been able to successfully condense a large amount of material into an understandable package. So the place to start, I guess, is with something that is called the Standard Model. What is this? Well, the Standard Model is sort of the cornerstone of modern particle physics. So this is a theory that people wrote down in and around the 1960s and the 1970s. And the idea behind the model is, so it's a quantum theory. And the idea is that you visualize everything that we know about in our world as a kind of field, or as a kind of particle, if you like. So it's a quantum theory, so you can have waves and particles sort of being conceptualized as the same thing in some sense. So you can see in this little picture that I have, this little table at the bottom of the slide, a kind of breakdown of all the different particles in the Standard Model. So these particles are hypothesized to exist. We can write them down. Here they are. So some of these you will no doubt be familiar with. So down on the bottom, you can see in green the electron, which is a very famous one. And then there's other particles called muons and taus, which are kind of like heavier analogs of electrons. And then you have quarks, which you might have heard about in purple. These are particles that sort of make up nucleons, so protons and neutrons. And then in red, you have another set of particles that actually mediate the interactions between these other two types of particles.
So Sam, a quick question.
Mm-hmm.
So you said that these were developed, or this Standard Model was developed in the 60s and 70s. Would it be that when these particles were quote unquote discovered, it's really a case of physicists looking at the world, particle physicists looking at the world and saying, okay, this just won't work unless we have a muon neutrino, and so they assign a mathematical property to that particle, and it helps them to explain how the things that they see work. Is that how these things would have been discovered?
Yes. So it kind of, these things were sort of discovered all in their own unique ways, but several of them were definitely discovered in that way. So for instance, neutrinos, the three particles on the bottom of the table, play a role in beta decay of nucleons. And so this is a process where, say, you can have a proton converting to a neutron, for instance. And so someone, I forget who exactly it was, maybe it was Pauli or someone like that, they sort of had this revelation that, here's this process that we don't really understand why it happens, but let's say such and such particle existed, let's say a muon neutrino, then we would have a mechanism for understanding why this is happening, and we would have a self-consistent theory that can explain it all. So they hypothesize the existence of this particle. They come up with some way to test, some independent way to test that other reactions show evidence for this particle's existence as well. And in this way, you can kind of confirm this prediction and build up your model particle by particle, if you like. Others were sort of discovered by people just thinking that it would make the theory more mathematically elegant if this particle existed, and then they make a prediction. You can go out and test it, and indeed find that it does exist. So each of these particles, I guess, would have its own slightly unique story for how it was discovered. But yes, it's very common to discover things in just the way that you've suggested. And in fact, the recent discovery of the Higgs boson over on the right of the table, which you might have heard about, this proceeded in exactly this way. Someone had some idea of how we could tie a few loose ends of the theory together if such and such particle existed, the Higgs boson. So you go look for it and you find that it does exist, and everyone's very happy because it ties loose ends together and it makes the theory more self-consistent.
Okay.
So I guess these particles that you see in this table, together with the interactions between them, are what comprises the standard model. And like I said, this is kind of the old faithful in particle physics. This is the model that all other models must somehow answer to, or must be able to replicate the predictions of, if they're to be taken seriously. So, of course, like I said, this model's been around since the 70s. We've tested it very well by now. We want to move forward. We want to improve our understanding of nature, and so we want to go beyond the standard model. There are quite a few open problems with the standard model. So reasons, it's not as though we have a complete theory of everything and physics is now over and we can all go home. Quite the opposite. There are a large number of holes in the standard model and things that it can't really explain. One such problem, which you might have heard about, is the existence of so-called dark matter. So there's no particle in the standard model that is a suitable candidate for whatever dark matter might be. So people are working very hard to understand, whether we can add some kind of new particle or maybe several new particles to explain this dark matter, and so on and so on. There are quite a large number of these kinds of problems that motivate people to actually do things like build a Large Hadron Collider and go ahead and try to find evidence for new physics models that will help improve our understanding of nature and help us model it better. So each of these new physics scenarios, of which there are hundreds and hundreds of them that are sort of hypothesized, they're all motivated by acting as a solution to one or several of these open problems. And the one sort of common thread between all these models is that the method by which you could go out and search for them is by searching for a new particle. You build a big detector, and you try to use that detector to detect this evidence of some new particle that you might be interested in for whatever reason. Say because it's predicted to exist by your favorite new physics model. So the question is, why do we need these huge detectors, such as the one that you see in the picture at the bottom of the slide? And I guess to give you some sense of the scale of this detector, the radius here is something like 11 meters. So and the length, I think, is something like 40 meters. So basically, this thing is like the size of a small building. The reason that we need these huge machines to detect these new particles is because producing these new particles requires a lot of energy. And this is, you can see that this is true by looking at the formula E equals mc squared. Typically, these particles in these new physics scenarios are very heavy, and therefore are very unstable and decay very quickly into other particles. And so because they are so heavy, one needs a lot of energy to produce this large amount of mass. And so we have beams of highly energetic particles that we collide into each other, and this allows us to create these very heavy exotic new particles that we're searching for.
And so, Sam, would you mind going back for just a second? So that's just the detector. That's where the collisions are engineered to take place. The actual whole Hadron Collider is a huge beast, but this is just the place where they smash together and where the changes or the new particles that are created are detected. Is that right?
That's right. That is exactly right. So if you look on my next slide here, you can see maybe a bit more of a complete picture of what's actually going on over in Geneva at this machine. So the Large Hadron Collider itself is this big, huge ring that you see at the bottom of my slide. So it's a 27-kilometer circumference proton-proton collider. And so what this means is that we have two beams of protons that go around this ring in opposite directions. And then we have, I guess there are 6, but I think the 4 main ones are just shown on this picture. So there are collision points where at 4 different points around this ring where we build detectors like this. And at the collision points, we flick these beams together very quickly, actually something like 40 million times per second at these collision points. And so this is where we sort of construct our detectors around these collision points, and then are able to measure the products that come out of these collisions. So like I say, there are 4 main detector experiments that are built at these collision points at the Large Hadron Collider. So the one I worked on is called ATLAS, which stands for a toroidal LHC apparatus. And the toroidal refers to basically the shape of a particular magnet system that the detector uses. So this is the kind of apparatus, if you like, that we're using to do these searches. We have these. We need to, in order to produce new particles, we need a lot of energy, and so we want to build these massive rings that let us accelerate protons, get them going around these 27-kilometer ring in opposite directions, and then we flick them together extremely quickly at 4 collision points, and we build massive detectors around these collision points that let us sort of see what is coming out of these collisions, and therefore either confirm or deny the predictions of various hypothesized physics models. So I mentioned that the detector experiment that I was working on was called ATLAS. And this is one of the general purpose particle detectors at the LHC. The collaboration is quite large, consisting of over 3,000 members from different institutions around the world. And the general design of the detector you can see in the bottom figure. The way that I always think of these particle detectors, and the design is generally pretty standard, at least conceptually for modern particle detectors. The way I always think of them is kind of like an onion skin. So the detector is comprised of a series of cylindrical layers, and each layer has a different purpose in terms of detecting particles. The first layer right in here is called the inner detector, and this goes from a radius right from the collision point out to about 1.2 meters. And we use this to make momentum measurements for charged particles that come out of the collisions. Then outside this kind of gray area here, we have our calorimeters, and these allow us to make energy measurements of the particles that are flying out. And this extends out to about 4.5 meters. And then outside of that, we have the third and final layer, which is most of what you see here in these rings at the end. And this is called a muon spectrometer. And so this is a specialized detector that allows us to make measurements of particles called muons, which I mentioned before. These guys right here, one of the standard model particles. Basically, it's like a kind of like a heavier electron. So how does this all work in practice? Well, you can see in this cartoon over on the side how we can actually use this onion skin layered detector design to build a complete picture of exactly what kinds of particles are flying out of these collisions. What this cartoon is showing you is basically what each type of particle, so photons, electrons, muons, protons, and neutrons, would look like to each of the layers of the detector. So this greenish layer right here, this tracking chamber, corresponds to this sort of yellowy part in here, the inner detector. So you can see that, say, for instance, electrons, charged particles, will leave tracks in this tracking chamber. Then outside that, the red and green, we have our calorimeters for measuring energy. So you can see that the different particles will leave certain characteristic shower shapes in these different calorimeter systems. And this allows us to...
Does that mean, Sam, that the particles are breaking up into subparticles when they branch out like that?
Yes, that is correct.
Or is that just a number of them that have branched out like that?
No, you are correct that it creates what's called a shower in the calorimeter. So this electron will come in, it'll pass through this tracking chamber and leave a track through that chamber, and then it will hit this calorimeter, and the calorimeter is more or less like just a big dense piece of lead. And so what happens is when the electron is incident on this material, it kind of fragments into a bunch of other electrons and photons, and it creates this big messy thing that we call a shower of particles. And so that's what all these little sort of tracks are meant to show here. And by kind of...
Is that what an electron breaks into, other electrons and photons, or was that just an example you were giving?
Nope, that is exactly what it will break into. So it'll decay into less energetic electrons by radiating photons, and then those photons can convert into pairs of electrons, and that all can happen iteratively, and it creates this big mess in the detector, in the calorimeter. And we have, so I mentioned that it's basically a big chunk of lead, and then more accurately, it's a big chunk of lead with kind of pieces of liquid or strips of liquid argon interspersed through this big chunk of lead, which lets us kind of measure the properties of this of this shower. So it lets us measure the degree of ionization of this material. And from that, we can sort of, there are complicated algorithms that you can use to extrapolate from the properties of the shower back to the energy of the incident electron that actually seeded the shower.
So the particles kind of turn on, they excite the gas, and that way the detector knows where the particles are?
Yeah, exactly. It knows both where they are and how energetic they are. So it lets us measure two things really at once.
Cool.
So yeah, and I mean, for the other detector layers, similarly, they interact with these different particles in different ways, and so it's almost like a kind of puzzle, if you like. Each of these particles leaves characteristic signatures in each layer of the detector, and by putting all of these together, we can infer what type of particle has actually passed through our detector in the first place. And not only that, we can infer its properties, like its momentum and its energy and things like that. So this is all all of this information is read out from our detector as electrical impulses, which we feed into huge clusters of computers. And these computers are sort of programmed with complicated algorithms that can interpret the different signatures that you're seeing in the different layers of the detector and extrapolate back to create a picture of what happened when the two protons collided, and which particles flew out in which direction, and what properties they had. So this is the kind of big picture of how we reconstruct proton collisions using one of these massive detectors.
So in the Hadron Collider, Sam, the protons are being sent in opposite directions. Then some type of magnet is used to direct them into each other, so they smash and cause these reactions. Would this be something that you zany physicists are doing every day, or would this be like, would these collisions only be made to happen once a year? Like how often does this occurrence happen in the run of the life of the Hadron Collider?
Well, so the beams collide with each other 40 million times per second.
Constantly, or do you
Constantly.
make that happen only once in a while?
Constantly. So that will it's not happening right now, actually, because the Large Hadron Collider is getting upgraded to be able to collide at higher energy. But when it's running, this is happening around the clock.
Oh, is that right? Okay, so it's not just something that you say, okay, today we're gonna collect some data, make the beams smash together and see what we get. It's actually happening all the time.
Yes. In principle, it's happening all the time. In practice, there will be a brief shutdown. Some equipment is malfunctioning, so we have to shut down for a while. But
it's just a massive amount of data then that's pouring out of this thing all the time.
Yeah, the amount of raw data is about a petabyte per second of data. Now this can be heavily reduced in many ways to make it more tractable, but the raw amount of data, if you wanted to try to write every piece of information coming out of the LHC, would be around 1 petabyte per second, which is ridiculous, really. So
why if these collisions are happening kind of nonstop during the operating life of the thing, why isn't just the same information being generated over and over again? Like, is something new being generated all the time? Or, I mean, you'd think you'd kind of get in a little bit of a rut and you'd be producing the same data over and over again.
Right. Well, that's an interesting question, and the answer is quantum mechanics, right? So what happens when these protons collide is not deterministic. It's in fact random because of quantum theory. So you can do calculations that tell you if I collide these protons at such and such energy, what's the probability that this will be what comes out of the collision? But that's the best you can do, right? And that's just quantum mechanics. So you can never predict with certainty for a given proton collision what will come out. And in fact, so the best we can do is to know what's the probability of different things coming out of my different collisions. And in fact, one of the big challenges of doing these kinds of experiments is that the stuff we already understand very well, like say the Standard Model, is vastly, vastly, vastly more probable than the new physics that we might be interested in. And I guess that's in some sense sort of by construction, because if the new physics models that we were interested in were much more probable than the Standard Model, then we would have already discovered them. But yeah, so it's the kinds of, let me skip ahead here this slide just to illustrate this point that's come up. What this graph here is basically showing you is you can think of the vertical axis as like a probability. So it's kind of like a probability of a particular type of particle coming out of a proton collision. So there's a particle called a W particle, a Z particle, top quarks, all different kinds of particles that can come out of proton collisions. And this vertical axis is kind of illustrating to you how probable these collisions might be. And you can see that, to give you a sense of the scale, the types of new physics scenarios that we're interested in typically are, in terms of probability, like would be down around 1 on this vertical axis or less. And the most probable outcome of a proton-proton collision at the LHC isn't even shown on this graph, but it would be somewhere at like 10 to the 12, say, on the vertical scale. So we're having to deal with,
and what would that be? What would be created in that instance?
So almost every collision that happens at the LHC is what we call produces what we call jets. And so a jet is, if I go back to my little table here, a jet is essentially just the production of one of these purple particles, or several of them, or this gluon right here. And so these are the particles that participate in what's called the strong force of nature. So quarks and gluons are overwhelmingly what is being produced by the LHC. And so if I look back here, so one example would be, you can look at these particles here, which are made up of quarks and gluons. This is called a pion. This is a proton, and the neutron as well. And you can see that they either pass through the tracking system and leave a track, or leave nothing at all until they get out to this hadron calorimeter where they shower. So most of the events that we see are going to look like a bunch of activity in this hadron calorimeter energy measuring device, and you won't see much of the electrons and photons and things like that. And there's not really, I don't think there's really an intuitive way to understand why that's true. It just happens to be the way it is. I mean, this strong force is called the strong force because it's completely dominant over the other interactions of nature.
And I take it that these really common occurrences or common results, common particles that are produced are kind of boring to you guys.
Yeah, exactly.
Okay.
So these are the kinds of events, of collision events, that would have been interesting to particle physicists in the 60s and in the 70s. And even in the 1980s, when some of these particles were still being discovered. This last quark, I guess, was discovered in 1995. But by now, these are all very, very, I guess, ho-hum type collision events that we don't really care about. And so one of the main problems is actually trying to deal with the fact that almost all of the events are these boring jet events with these strong interactions, and we need to come up with clever ways to filter out all of this junk that we don't care about, and get to the much rarer hypothetical new physics type events. But we have to get rid of these boring events in such a way where we are being careful not to sweep away these potentially interesting events, which are much, much rarer. So this is actually really somehow the central problem of experimental particle physics, is trying to come up with clever ways of identifying. It's essentially a signal versus background problem, where you have an overwhelming background and a comparatively much rarer signal, and you need to dig out this signal over this enormous background that is 10 to the 12 times more common.
Software filters are stuff that you would write to clean up the data.
Yeah, so some of it is software, and in fact, we have some of it is hardware even. So there are people that spend their whole careers working on this particular problem, and we have at Atlas we have what's called a trigger system, and it takes this raw output of this colossal number of events, and it sort of filters it from one level to another level to another level, and then each level somehow cuts out more and more events and is increasingly sophisticated in the types of algorithms that it can use to filter out all of these events. So yeah, it's a huge problem, and a huge amount of effort gets invested into trying to deal with exactly this issue. So this slide here is very text heavy, and I apologize for that, but I guess what I want to do is just kind of go step by step through the big idea of how we search for a new physics model at a hadron collider. And I think the basic idea is actually surprisingly very simple, of sort of the underlying philosophy of this kind of an analysis. So I've covered parts of it so far, but now I'd like to try to tie it together and complete the picture of what the overarching philosophy is of people who work on these kinds of analyses at these colliders. So proton collisions produce huge numbers of particles which spray out into our huge detector that we've built. And as I mentioned, these particles produce electrical signals in different parts of our detector, and we're able to interpret these signals and extrapolate backwards to reconstruct or understand which particles pass through and what kinds of properties these particles might have. So what can we do with that information? Well, the idea is that you have some new physics model that makes some kind of prediction. And in particular, the prediction that we're interested in is that you have a hadron collider and you're going to collide protons together. What type and with what frequency of particles we should be seeing from our proton-proton collisions. So maybe your new model predicts that we're going to see more electrons than we would see if it was just the standard model in nature. So you need to have some testable prediction about the type of particles that are coming out of your collisions and how frequently these particles are coming out, or what properties they might have. So the idea is then you have your hypothesized model. You understand something about what kinds of predictions it's making about what you should see in your data. And then what you want to do is go into your data set and start selecting collisions of this type. So say, let's take a simple example. Let's say I come up with a new physics scenario, and it predicts the existence of some new particle, and let's say that this new particle, I should see it in my detector, and it should have a momentum of some number. So let's say it should have a momentum of 5 GeV or something. That's just a unit of momentum. So my model makes a prediction that there exists a new particle, and if I have the Large Hadron Collider, I collide protons, I should produce this particle, and it should have a momentum of something like 5 GeV. So what I would then do is I would go into my data, and I would try to pick out collisions that had, let's say, lots of particles with momenta around 5 GeV. So what I could then do is then I have a sample of my data that I've enriched with collisions featuring products that have particles with momentum of around 5 GeV, let's say. And what I could do is I could take that data set. So what I could do is then I could take my standard model and I could do a calculation. I could say how many particles at the Large Hadron Collider, if the standard model is the true theory of nature, how many collisions should I expect to extract from my data set that have particles with momenta of around 5 GeV. So I can come up with a number. Let's say the standard model predicted that in my data set, I should see around 100 collisions with particles with this momentum. So what I can do is I can then go to my data set and compare how many collisions I did select to the prediction of the standard model. So let's say that the standard model predicted that I would see 100. Let's say that in my data, I see 1,000. So I see way more than the standard model predicted in my data. What this either means is that the standard model is wrong, and there's some new physics model which is contributing these excess particles that I'm observing, or maybe all it means is that I didn't do a very good job of estimating the standard model prediction, and that also can be the case. So this is somehow the central idea here. You have you do hard work to understand the standard model, and you do hard work to understand your new physics model or your signal. And so here the standard model is kind of treated as background, and your new physics model is treated as signal. So you do hard work to understand the predictions of each of these models and how many events, how many collision events they should each be contributing. And then you just go and take your data set. You select out the events of the type that you're interested in, and you compare. You compare the prediction of the standard model alone against data, and you compare the prediction of the standard model plus your new physics hypothesis against data, and you see which one models the data better. And this is basically the entire idea of experimental particle physics. So it's the idea is, you know, it's all about comparing your. I mean, it's in some sense it's exactly what you would expect, right? You have some model and you're just trying to compare it to data and see how well it models the data versus some other alternate hypothesis, which for us is the standard model. So I guess this kind of links back now to the challenge that we talked about before, where the big challenge that isn't obvious from what I just said is the fact that the background generally turns out to be overwhelmingly more probable than the signal. And so it's sort of like looking for a needle in a haystack, trying to understand whether or not you're observing these signal events. And so in practice, it requires a lot of very careful statistics to sort of dig out what your results mean and how you can interpret them. But I would say that's the broad strokes of the whole field of experimental particle physics. That's what we're doing. We are accumulating these data sets and trying to quantify how well we can model what we're seeing in these data. And from that, infer whether or not there might be something new in the data that isn't accounted for by our model. So this slide now that you're looking at is showing you a particular example of a new type of physics model that you might be interested in looking for. And so this was the model that I spent a lot of effort searching for over the past few years, or I guess one of the models. And this is an extra dimensions model. So it's kind of interesting in that if this scenario was true, and it doesn't look like it is actually, but if it was true, and this is what nature was really like, it's modeled by the equations of this theory, then we would be living in a world where we have more than 4 dimensions. So the world around us, we always like to think of it as being 4-dimensional. So one time dimension and then 3 space dimensions. But it turns out that if you can write down theories of nature where you have more dimensions than just these 4, and this ends up helping you solve a lot of different problems with the standard model. So I guess the kind of central idea of how we might look for a model with extra dimensions in it would be, I guess, in a perfect world where you don't have any extra dimensions, what happens in your collision is you prepare these beams of protons, you know how much energy they have, you collide them together, the products of the collision go out into your detector, you can reconstruct all of these collisions, measure the energy, and the amount of energy that you reconstruct and measure should be exactly the same as the initial energy in your beams, and that's because of energy conservation. Now, if you have extra dimensions, however, what you can have is after your collision, after the proton collision, some particles might escape off into these extra dimensions of space and will not show up in your detector. So you'll be able to measure an actual imbalance of energy between from what the initial energy that you put into the collision was and what you end up measuring at the end of the day in your detector. So we call this missing energy. And so you can have different extra dimension scenarios will make very definite predictions about exactly how much missing energy we should expect to see in our collisions. So this is how, just to give you an example of how, what one of these new physics models that I talked about might look like in terms of a detector signature. So what we would see is we would see collisions proceeding as normal, protons come in, a bunch of stuff comes out, but then down the road when we reconstruct these collisions in our detector, we would find, oh wait, there's a bunch of energy here that we're not seeing in our detector. Where did it go? And the idea is that these particles have escaped off into some extra dimension of space, and we are therefore not measuring them in our detector.
Sam, I'm deliberately holding back my questions now because I want to make sure that you get through your information in a reasonable amount of time. But I just have to ask you, it almost seems like this concept of extra dimensions turns this whole thing into a almost intractable problem, where you just say, oh, well, I didn't quite get what I expected. I guess that particle just went into another dimension. I mean, it just, how do you solve that problem?
Yeah, no, that's a good point. And I guess I've kind of tried to streamline it a little bit, but there's a lot of other considerations that come into play. So, for instance, a lot of work goes into validating the different detector components. So we have like an extremely precise understanding of how all of these detectors behave, and we do that by shooting test beams into them and probing them in all kinds of different ways and understanding their response. So that's one thing that we do. to ensure that this missing energy that we would be seeing is in fact something real. There are also, it's also not just as simple as the missing energy. So for instance, you have, in all these models, you have very detailed predictions about what kinds of distributions of different quantities that you measure should be and what the resolution of those should be in your detector. So you have like, it's not as though, it's not quite as simple as, oh, everything looks normal, but yet I'm missing some energy. It's also, I'm missing, such and such amount of energy, but I also have a definite prediction about what the the distribution of the momenta of different electrons in my events should be, and I can plot that distribution and compare that to the prediction of my model. And
okay, so you're saying that the momenta of, say, electrons, that's actually also a function of all the other particles. So you have ways of testing whether there's other particles present, even though you don't see them.
Right. Exactly. That's exactly right. So the different properties, like the kinematic properties of these collision events, like the momentum, the direction that the particles are coming out in, are all definite predictions of these models. So it's sort of, if you do see evidence of something new, you can build up an extremely compelling picture of what it is by hanging all of these confirmed predictions together. So
okay, I promise to hold back on the questions, but I'm not doing so good, but so well. But just out of curiosity, do you ever see a signal where, say, the momenta of electrons or other particles is going one way, and then all of a sudden it changes, and that might be evidence that a particle is, that another, maybe a more massive particle has flipped into another dimension? Does it still have mass, for example, that's recognized by other particles if it moves into another dimension?
Yes. So it really depends on what model you're talking about. The kind of ridiculous thing about particle physics is that we have so many different ideas of what a new physics model could be, is that what you can somehow dream up a model that can do a lot of different things, right? You can dream up models that can have different properties and can do can make things behave in many different ways. So for instance, just in the world of extra dimensions, there are models. There's probably about 5 to 10 different main classes of extra dimensions models, and each of these would have different types of signatures. So they might have extra massive particles. They might predict extra massless particles, and these particles might then decay into other different types of particles. And so it's kind of in principle, you can dream up a model that can do whatever you want. And then I guess the thing to mention, that fact might worry you and might bring you back to your other question about how do we know what we're even seeing if we can have all these models that can just do whatever we want? We can say any anomaly we see in the data, we can dream up some model for it. Well, the thing is that the parameters of these different models end up being heavily constrained by already existing data. So it's like I said, we understand the standard model really well, and we've been testing it very precisely, like since the 60s and 70s. And so it's actually, although in principle you can think up a model that in a vacuum, in a not considering any existing data, can do whatever you want. Could have some massive particle decaying to some electrons and some wacky stuff. But in fact, it's quite difficult to dream up a new model that is able to accommodate all of our existing data in a satisfactory way. So the types of models that are actually realistic Anything is kind of mathematically possible, but in order to be taken seriously and to be considered realistic, you have to be able to account for, like 50 years of particle physics data, which turns out to be quite a difficult thing to do. So many models actually die after some guy will write a theoretical physics paper about some model that he just dreamt up, and everything looks great, but then a couple of years later, someone realizes, oh wait, your model, the equations of your model make this kind of a prediction, and this is actually in conflict with a bunch of data that we already have from the 80s or something. So there's an interplay involved between experiment and theory, which sort of keeps everyone grounded and keeps everyone focused on moving things forward into the realm of plausible models. So I mentioned that the strategy here for your analysis is to select signal-like events and to reject standard model-like background events. And so the way that this is done is by identifying the properties of your signal-like events, say the different types of particles and the different momenta and energies and directions that they might have, and then cutting up your data set to only include collision events that have these sorts of properties, and so therefore might be signal events. Now, they could still, in fact, be background events that are just that sort of look like signal events in your detector, but there's nothing really that you can do about that. All you can do is try to select these signal-like events, and then try to understand your backgrounds very well, so that you can have some prediction for how many of these background-like events you should see, and then be able to compare the data at the end of the day and see how well you're doing, see how well you're modeling reality. This slide is kind of all this is really showing is that you can look. So these axes are it's a 2-parameter new physics scenario. It's in fact masses of 2 hypothetical new particles, and the colors are showing statistical significance. So you can see that in this top picture, we have a certain way of cutting up the data and trying to pick signal-like events and reject background events. And this is giving us very strong sensitivity along this kind of diagonal region, you can see. And then in the bottom picture, we have a different way of cutting up the data, a different way of trying to select signal-like events over background events. And you can see that using this algorithm for cutting up the data, we end up having much stronger sensitivity out into this lower region. And so I guess all I wanted to convey, this slide has a lot of information on it, but all I really wanted to convey is that the way that we quantify how well we are separating signal and background like events is by making plots like this across our model parameter spaces and seeing what kind of statistical significance we're getting in terms of our separation of signal and background. And so we in this way, we're able to see how well we're doing when we're designing our analysis as we go along. A lot of effort goes into understanding and modeling our standard model background. This is in many ways the real key to a particle physics analysis, is to understand your backgrounds very well. And I guess the idea here is it comes back to what I was talking about towards the beginning of the idea of comparing your background standard model background prediction to your data and seeing how close they are. So if you're seeing thousands more events in your data sample than you're predicting from your standard model, then it's either indicative of the fact that there's some new physics that you weren't modeling that's producing all these extra events that you weren't expecting, or that you've done a poor job of modeling your background. And of course, if you want to be able to conclude that all these extra events are in fact coming from some new physics model, you need to be able to convince people that in fact you have done a very good job of modeling your background, and therefore that you know these extra events are real new physics events. So a lot of effort goes into background modeling, and this is, like I say, one of the whole keys of the analysis is really getting a good handle on your backgrounds. So this slide also has a ton of information, but I wanted to just flash it up just to show you that another big consideration in these sorts of analyses is uncertainty. So we have a lot of sources of systematic uncertainty that creep in terms of understanding our detector and understanding the software that we're using to perform these analyses. And so we do a very careful job of going through and cataloging and computing each source of uncertainty, and then understanding what kind of an effect this has on our final result. So this slide here is I guess, the bottom line of the particular analysis that I worked on. So what you're seeing here, the columns of this table are different selections or different algorithms that we used to distinguish signal from background. So we have 1, 2, 3, 4, 5, 6, 7 of these. And so we have seven different algorithms that we use to cut up our data and try to distinguish signal from background. And the rows that I'll draw your attention to are highlighted in this green rectangle. So the top one, sum standard model, is our background prediction. So what is this? Well, this is for each selection algorithm, we have done a calculation which says if the standard model is all that's out there in nature, if that is reality, the standard model, here's how many events we should see in our data for each algorithm, for each selection algorithm. So let's look at this first one. So with this particular selection algorithm, if the standard model is reality and there's no new physics out there, we should expect to see 96 plus or minus 20 events in our data when we go ahead and look at the data. Now, the bottom row is then what we in fact did see in the data. So this 96 plus minus 19 was our prediction if the standard model is reality. What we saw in the data was a 101. So that's well within uncertainty. So we certainly cannot conclude from this that there's some new physics producing extra events that we don't understand. I mean, imagine what would have happened if this data number here was, say, 1,000. Then our background only prediction, our standard model only prediction, is around 100. And if we're seeing 1,000 in data, then like I said before, either we've done a horrible job of estimating our standard model contribution, or there's some new physics model out there that is contributing 900 extra events that we didn't expect to see. So that's how one would make a discovery if there was a new physics model present. But clearly, you can compare the other numbers for prediction from the standard model versus data, standard model versus data, and if you look across, all of them are in extremely good agreement with our standard model predictions. So we can compute p-values to kind of quantify that agreement, and that's what you see in this row.
Sam, my simplistic read of that is that nothing beyond the standard model is required to explain what we see.
That's right. That's completely right. So the outcome of my work was a null result. So I did not find evidence of a new physics, right? The results that I obtained are in perfect agreement with the standard model. So there's no evidence here of a new physics model at play. And in fact, with the exception of the Higgs analyses at the LHC, everyone's analysis looks exactly like this, where we have remarkable agreement between our standard model predictions and our data. So far, the LHC analyses have actually been very boring because no one has found any evidence yet for anything new. So it's a bit disappointing, actually. It's quite disappointing because a lot of people hoped that as soon as we turned on the LHC, we were going to start seeing all of these new physics signals that we had never dreamt of before, or that we had been dreaming of for many years. But in fact,
just because you were able to bash protons together with so much more energy than was previously done, they thought that they would produce new particles or new results.
So remember this E equals mc squared thing that I talked about. So if you have some model, basically if you have some model that predicts the existence of a new particle with mass m, in order to create that particle in a laboratory, you're going to need more energy, right? Because energy and mass are somehow essentially the same thing. So to produce more and more massive particles, you need more and more energy. So this LHC gave us much more energy to work with. So people were hoping that with all this extra energy that we'd never had access to before in the laboratory, that we'd be able to make new massive particles that we had never been able to produce before. But in fact, that is not the case, and we haven't seen anything new. I guess aside from the Higgs, but I think to most particle physicists, Higgs isn't really considered something new. It would be more new if we hadn't found the Higgs. In fact, it would be more unexpected from a particle physics standpoint.
Well, Sam, you better tell us something to justify the billions of dollars that have been spent on this thing.
Well, I wish I could, honestly. I wish I could, but honestly, I mean, it's bleak at this point. It's important that we found the Higgs. That's a big deal, right? Because that's the last particle that we needed to find for the standard model. But like I say, most people believe that the Higgs was there already, and it was no big shock that we actually confirmed its existence at roughly the mass that we expected it to be at. But in terms of more exotic models like extra dimensions, or maybe you've heard about supersymmetry or things like this, there has been so far no evidence at all. So people are worried. Physicists are starting to get worried because, yeah, we've convinced our government to give us tons of money to build this big machine, and so far we haven't been able to actually discover anything new with it. Now, it's not completely bleak because actually, I think I mentioned before, the LHC is in shutdown mode right now, and it's being upgraded. So starting in, I think, sometime in 2015, the LHC will come back online with even more energy than we have now, or that we had previously when I was doing my research. So that will give us a much larger reach, actually, than we've been able to have so far in terms of energy. So a lot of people a lot of physicists are hopeful that once we are able to use the full potential of the LHC and get it ramped up to its full energy, that we will in fact see evidence for some new physics models. But I guess that remains to be seen. We'll see whether or not we end up discovering something.
And what is it possible, Sam, that even if there's particles out there that haven't been discovered that are important particles that are part of what you have called dark matter, that they could still exist within the operating range of the standard model? And so they might be really important. They might have, I don't know what I'm trying to say. They might be important, but they just might not be measurable within the experiment in some way.
Yep, I mean, it is possible. I mean, maybe there's some extra force that we haven't yet discovered in nature, right? And maybe that is not at all reflected in the standard model. We don't know what happens at nature in nature past a certain energy scale. We really have we don't have a good idea. You know, we can probe with our experiments up to energies around around where we currently are with the LHC, and after that, we have lots of good ideas that are motivated for various reasons about what might happen, but you know, we don't know for sure. So yeah, it's quite possible that I mean, one interesting thing that I've heard some people say is that is nature queerer than we suppose, or queerer than we can suppose, which I always thought was kind of funny, because yeah, maybe, you know, maybe there's some wild aspect of nature out there that we are so far away from understanding that it's hopeless. We don't know. All we can do is we have the standard model, and the standard model works incredibly well for for the kinds of experiments that we've done, and the kinds of predictions that we've used it to make. I mean, it works incredibly well. The standard model can make so the most precisely measured quantity in all of science is something called the G factor of the muon, and this is something that's predicted in the framework of the standard model, and we've managed to predict this accurately and compare with experiment to 9 decimal places. So it's the kind of agreement between model and data that we're getting with the standard model is quite remarkable. But I think probably we have at best a huge distance to go before we have a you know, some kind of theory of everything, and at worst we have infinity to go, and we can never get there. But I guess that's sort of a matter of opinion, I guess. Depends on who you talk to, how they feel about that question.
Mm-hmm.
So let me try to kind of tie this up quickly here. So what you see on this slide is I guess this is, so I mentioned early on in my talk that what we do here is we try to perform some kind of statistical analysis, so that even if we do obtain a null result like this, we can still get some use out of that, and we can try to say something new using that null result. And so what you see on the vertical and horizontal axes on this plot are 2 different masses for 2 new particles in this extra dimensions scenario, roughly. And what this line is showing you is a 95% confidence level limit on the parameter space of this model. So what does that mean? Basically, what it means is that the results of our analysis imply that the masses of these 2 particles, this horizontal and vertical axes, cannot be anywhere in this portion of this figure at the 95% confidence level. So the results of our analysis imply that this model could still in fact be real if the masses of these particles sit somewhere outside that red curve. And so the reason for that is that as the particles become heavier and heavier, the LHC is no longer energetic enough to actually produce them, so we can't really say much about whether or not this model is true once that happens. We can only comment on, you know, on the fact that if the particles are massive enough for us to produce them at the LHC and we don't see them, then we're going to rule out this model. So that's that's kind of this plot is sort of the final plot of the analysis, I guess, the interpretation plot. We call this a limit plot. So I guess I've talked about the simplest search strategy a lot for new physics at hadron colliders. And that is the general philosophy is to understand your new model, understand your standard model backgrounds, and then compare the predictions of these 2 cases with data and try to see if you're seeing some excess over your standard model prediction in the data. And as I mentioned, at the LHC so far, we haven't seen any significant excesses in any of our beyond the standard model analyses. But all is not lost, because we can use these null results to place 95% confidence level limits on parameter spaces of these new physics scenarios, which helps us understand, you know, I guess, domains of plausibility, if you like, of where new physics might still be lurking, and helps us understand where we should focus now if we want to move forward and try to discover new physics. And although we haven't seen any conclusive signals yet of new physics, the hope is that next year, when we crank up the energy of the LHC, that we are then going to have enough energy to hopefully produce some highly massive new particles. But the jury is still out on that, and it will be quite interesting, I think, to watch and see how that goes, and whether or not we actually do discover something new. So thanks a lot.
Oh, thank you, Sam. I have a ton of questions for you, but I think we've gone a little bit over time, so I'm going to hang on to those questions and keep them for some time later, hopefully over a beer. And but I really thank you for laying this out so clearly. You and I have talked about this a lot. I've asked you a lot of questions about it, but I don't think I've ever quite understood it as well as I do now. And it was thanks a lot for a very clear